shown. I hope I made it fluid so that you could follow it and understand. It's an interesting topic for everybody, even for HF, but it's mostly focused on VHF. Why? Because you will see why. One disclaimer, so it's all the radiation patterns are shown in free space. It's not that I wouldn't know that we don't have free space here on the Earth. It's just they are much clearer to see. Right? The antenna radiation pattern is changed by the presence of the ground only in the vertical plane. And we are not talking about the vertical radiation pattern here, but how the radiation pattern looks like in a horizontal plane. So everything is valid when you put the antennas above the ground, with what I will show, but just for the clarity, okay? So it's about 2-meter contesting. So you start the contest by choosing a location first, right? You choose a location, and then you would, this is Snezhnik, right? Sugar 50 Charlie operated in the last September contest here. And then you would put first one antenna. But today, that was 4 years back, right? Today you wouldn't start with one antenna, you would start with 2 antennas, of course. And then you see your competition is having more antennas. You add third antenna, and then of course you have also YU stations there which are more or less present. You need to be present there, so you put 4th antenna, and then 5th and 6th. And at some point, it looks like that, right? It's a mess, nobody knows who kopije, ko plaća. It becomes very complex and complicated. Now let's go from the beginning. You have one direction. Okay, and what does it mean when you add the second direction? I will talk about the directions here. You add antenna, whatever kind of antenna for the second direction. So if it's one direction, it's clear, right? TX, RX, that's the radiation pattern. If it's 2 directions, okay, for the RX, normally for RX you put a switch there. Either you listen to this antenna or you listen to that antenna. So in each case, you have the same radiation pattern, same gains, everything is the same, okay? But what does it mean for the TX? Now on the TX, you would put a power divider there, you put 2 cables, and you have 2 antennas radiating at the same time, the same signal, right? The source is the same source, same transmitter, and this is how the radiation pattern looks like. So what's the difference? This is on TX, this is on RX, right? Is there any difference? Almost no difference, right? So you have 2 radiation patterns of the same form, of the same shape. You would say it's not a big deal. Actually, it's not a big deal when you have 2 antennas only. In this case, they are in opposite directions, but you could go 90 degrees, it's still no big deal. So, and it's valid also for HF, where you have 2 directions, more or less, that's what you are concerned about. But on VHF, antennas have much higher directivity. I mean, even the largest antenna on HF is still short Yagi, right? Now on VHF, you have larger directivity, you need more gain, and you need more antennas at some point, right? Because you cannot win a contest today with 2 antennas, right? You cannot win a contest with 2 antennas, and you cannot win the contest by splitting your power on half for each antenna. So what do? You start adding antennas, you start adding power amplifiers, and you start growing your station. Now, so you add power amplifiers, you add dividers, some cables, you put antennas with some, this is just thought up, right? So with some space between them, 20 meters, 10, 5, whatever the geographical location, conditions on your locations allow. You start putting antennas on it, and it pays, right? You make greater score. Your score is going up, so you say, it's fine, let's continue. But, and then you continue analyzing things, right? So you would start inspecting your azimuth QSO distribution chart to see where to put your antennas. Okay, this is from S59WW for the last September contest. This is how it looks like. So you say, okay, I will put 1 antenna for Oscar Kilo, 1 antenna for Oscar Mike, for Germany, of course. I need something for YULZ. And then I have Italy, the highest part of it, which is northern Italy, but there are also stations on the southern Italy. So you come up with 6 antennas. You say, I will split the antennas like that. These are my directions. Montenegro, yes, yes, I will put special antenna for you, but never worked you before, yes. Yes, next time. Okay, so I will show you how it, so the next few slides is going about the S59 delta echo mic location. How would it look like transmit radiation pattern when you set antennas like that? Okay, these are the antennas on our site. These are facing Italy 0. Here is Italy 1 you don't see. This is Oscar Kilo, Oscar Mike, Yankee uniform, and the top one which goes to Delta Lima. Okay, and so we will focus only on one hemisphere, only for Delta Lima, Oscar Kilo, Oscar Mike, and YU directions. I will tell you, you will see why. I focused only on this one. So these are the antennas we use. Okay, so we use this is fully rotable 2 times 5 lambda array, vertical stack, which is pointed to 315, which is for us Delta Lima. Then we have a fixed 4 times 7 element stack for Oscar Kilo, the same one for Oscar Mike. And then 10 meters away, there's another pole where we have 2 4 lambda Yagis vertically stacked, okay? So you can see all the antennas have approximately the same gain, which is what you want, also for the receive side. Approximately the same gain you need. Different directions. Now, and this is one important factor, antenna cables are of random length. And how does the TX radiation pattern looks like? See. Okay, something like that. And what did we want to see like? Like that, right? So what do we see here? YU direction, it's fine, right? It has some ripple inside, but it's like we wanted to beam there. Oscar Mike looks fine. Delta Lima looks fine. Oscar Kilo is strange, right? There's some notch here, and this notch also, we didn't want to have this notch here. So these antennas are all, so the simulation here was like you have the equal phase on all 4 antennas. But in practice, you don't have it like that. Now, one additional information from this picture, which I will refer to it in future slides. So the antennas for Oscar Kilo, Oscar Mike, they are having a crossing point at -3 dB. Delta Lima and Oscar Kilo at -6, and this is -10. So remember these 3 figures, which are important when you start stacking more antennas in different directions. Now, so this is the radiation pattern if all antennas are in phase. But let's say you don't control the cable lengths, right? So you put 2 cables are 1 meter longer, or 1 electrical meter longer, so just out of phase. What happens when they are out of phase? Okay? So Oscar Kilo, Oscar Mike are out of phase, for example. Randomly, you put it out of phase. So suddenly you have a huge notch, about 10 dB notch in this direction, which you don't want to have the notch there when you're transmitting, right? On the receive side, you receive on each antenna individually. The radiation pattern stays the same, but on the transmit side, you create a notch here, which you didn't plan to, right? Now, the YU antenna is fine, still quite the same. Delta Lima is also fine. But that's not what you want. So if you start playing with the phases of these 4 directions, I just put 3 diagrams, you can get different shapes of your radiation pattern, right? Different shapes. And this is all random. If you don't control the phases, it's really random. You don't really know what you transmit and where you transmit. Now you would say, okay, this is all theoretical simulations, right? You put exactly the same output power to each antenna. Of course, when it's out of phase, it will cancel. But in practice, I never operate the same power. You know, it's not like that. But it doesn't matter. The power doesn't really matter because the radiated field is shaped by the radiation pattern, and at some angle, you will have the same power, exactly the same power, and if opposite phase, it will create a notch. So this is an example where you put 3 dB more power to delta lima antenna, and you see this notch just moved a bit, maybe by 5 degrees somewhere, right? So it doesn't matter what the power level is. It's all about the phases. Okay, so for example, now that we have this delta lima antenna is rotatable, right? Listen, there's a station calling you from this direction. So you go and you turn your antenna for the receiving reasons, you turn it by 20 degrees to north. Now the transmit radiation pattern looks like that. This node just goes more to the right. Again, it would depend on the phases, but for this particular case, it looks like that. And what's also interesting to see, so this was the original radiation pattern, and you should know how these simulation tools work. They take the spatial direction of maximum gain and then normalize the gain, right? So this gain is now in horizontal plane, and the maximum gain is in horizontal plane. Now you turn this delta lima antenna by 20 dB, and you see you're losing 3 dB of gain. How come, right? Because the max of the gain is not in horizontal plane in this case. Why not? Okay, this is what you would like to see. That's why I showed here, because you are overlapping now more than by 3 dB these two antennas. And when you do overlap in the situation as in our case, you create let's say a notch in the vertical plane, right? So this is, okay, it's hard to explain, but in this direction, right? But, yeah, in this direction, the beam in the vertical plane splits. It splits why? Because this is how the stack is like. So this antenna is over the Oscar kilo antenna, and it creates a vertical stack, uncontrolled vertical stack. We have about 7 meters separation, uncontrolled phases, and this is like you would be making an array of 2 antennas, but you wouldn't care about whether, like a vertical array of 2 antennas, but you don't care about the phases and about the distance. And if it's wrong, you create this notch in the vertical direction. It's only 3 dB. Okay, it's only 3 dB. Who cares? But if I would say why you take 2 kilowatt amplifier, take 1 kilowatt, it's only 3 dB, you will say, oh, no. It's a lot, right? It can be even worse. Of course, it can be worse. So this is how it looks like this in 3 dB, in 3D, this split of the radiation pattern, right? In that direction, only in that direction. Now, if it turns out you make this contact with this station and you forget that you left the antenna there, you left it for, I don't know, for half an hour, and you are not working QSOs there, maybe because you have distorted your transmit radiation pattern. You have a great null here. Nobody hears you, or almost nobody hears you, even if you have much higher power. So you should be careful. Okay, so what are the general rules to observe? I summarize these rules. First rule, which I haven't talked yet, do not cross directions. It means never put antennas, whatever kind of antennas you have, that would cross the direction if they are on the same, approximately the same height above the ground. So this will hurt not only your transmit pattern, but also receive gain. So never do like that. Turn this antenna there and this antenna there, or this antenna should be much higher than that antenna. Much higher, it means it depends on the distance, right? If it's on the same tower, it could be just 2 or 3 meters higher. But if it's 10 meters or 20 meters away, you should take care about this, how this vertical radiation pattern looks like, and you can calculate what would be the height difference, but it's 10 to 20 meters higher. Okay, the rule number 2, never overlap antennas at 3 dB angle unless you control the phase. Because if you don't control the phase, you will get a null here. Overlapping at 6 dB, it's some distortion of the transmit pattern, but let's say it can be considered fine or safe enough. And if you are at 10 dB, it's safe, right? Because at 10 dB, it means that in this direction, you're not planning to transmit any useful signal, so it doesn't matter how much it distorts the radiation pattern here. And rule number 5, right? When you have one fully rotatable high-gain antenna, take care not to leave it for long periods of time beaming to the same direction as other antennas. So one solution to this is that you feed much more power to that antenna, so this null in vertical radiation pattern is just, it's not 20 dB or 10 dB or 15 dB, it's just 2 dB, 3 dB, because you have much this split in the signal level. So these are the 5 rules you should be aware of when you're operating, I would say, with 4 antenna systems or more, even with 2 if you want to push just into one direction, right? You should take care about this. Okay, now we go to part 2. Part 2 would be how you could fix it, or why it happens like that and how does it look like. Now let's start with a regular vertical stack. You stack 2 antennas vertically to get gain. You put them to the distance as required. You put them on the same tower, which goes approximately at the middle of the, let's say, gravitational center of the antennas. 2 phased cables. You know that they need to be exactly the same length, right? Everybody knows this. And then you get your antenna, which has the same radiation pattern shape in horizontal plane, and the gain you get by concentrating the power into vertical plane. So the beam width in the vertical plane is narrower, and you have this 3 dB of the gain. So here are the 3 numbers. Again, 3 dB, 6 dB, and 10 dB beam width of this antenna in horizontal plane. So what happens if you rotate the antennas or displace them angularly by 3 dB beam width? So plus minus 14 degrees on the same tower, same in-phase feeding, you get some funny radiation pattern. The gain drops, of course, because you are splitting the power now in 2 different directions, but still it looks fine, right? Now if you go to 6 dB, so the angle separation is 6 dB, 36 degrees apart. So these 2 antennas just overlap at 6 dB angle. And you can see you increased the 3 dB beam width increased almost by 3 times. Gain, of course, drops by 6 dB. And now if you go to the 10 dB offset, you start seeing 2 individual radiation patterns as we shown in the first or the second slide. In this direction, there is some transmit signal present, but you don't care actually, because if this is 10 dB down, it's like you don't expect anybody to hear you from this direction, so you don't care about this. You have 2 antennas, 2 radiation patterns. Because you're splitting the power down, it's additional 3 dB down, but it looks fine. Now, so how does it look when you don't control the phase, right? If you would put these 2 antennas plus minus 14 degrees apart, and you would feed them out of phase, you get something like that in horizontal radiation pattern. We have the great null here. The same goes for 6 dB, and the same goes for 10 dB angled stacking. So, now to cover a wide angle with 2 antennas, a wide azimuth angle with 2 antennas, you should overlap at 6 dB, not at 3, at 6, because you get this nice shape in the horizontal plane. So this kind of radiation pattern has a 3 dB angle at approximately 2 times 6 dB angle of individual antenna, and so on and so on. And there's one big but, right? It's one big but, and this big but is called antenna phase center. So nobody, as I would be aware, would put the antennas like that on the tower, but you could, right? So you say, okay, I put one. This would be one vertical stack here, and then I put another vertical stack 10 meters away, right? And you say, and one would think, okay, I will get the same kind of radiation pattern. But you don't, right? You don't. So when you split the antennas physically, something happens. And this what happens is actually making some distortion in your radiation pattern. So this 10 meters is just arbitrary. You can go like that, right? The distortion is similar. This notch moves a bit. You could go even 100 meters away, right? You can put this antenna 100 meters away, 100 meters of a cable. You will still get this kind of radiation pattern distortions. Why? Because this radiation pattern is electrical field distribution in far field. Far field of the antenna is, for this case, maybe 200 meters away. In this case, it would be 1 kilometer away because you're far away. You are creating a great distance array. And in the far 1 kilometer away, it doesn't really matter what you do with the separation of the antennas. You will always get the similar kind of a distortion. The only difference between 10 meters and 100 meters here is you see that this ripple is has more angle. The angle separation of the ripple is lower than what you would get here, for example. And that's because at 100 meters, the phase changes faster. So, as I said, the butt, this big butt is actually the antenna phase center. The antenna phase center is something that amateur radios don't talk about and don't know about because it's not important. In most of the cases, it's not important, right? When you make a vertical stack, you already put antennas to the same pole, same tower. You take care that phase center is for all the antennas at the same vertical axis. Now you should know, you should know that phase center of a short Yagi antenna is close to the center of the boom. Long Yagi antennas actually don't have a fixed phase center. The phase center is like more an area, maybe 50 centimeters or something somewhere. It's not a fixed point. So how does it look when you take a short Yagi? Okay, short Yagi is 2 wavelength Yagi. 1.5 wavelength Yagi, 7-element Yagi, 2.8 meter boom. These are the 2 distinctive beam widths, 42 and 60 degrees. You mount on the same pole at the phase center. You offset them by 60 degrees for the angle of 6 dB angle, and you get this kind of radiation pattern. Very nice, right? It's like perfect, and actually you get like that. From the individual antenna which has 3 dB of 42, you get an antenna which has 3 dB of 104, 2.5 times wider. Now, you can do this for 2 directions. Because for 2 directions, as we said, you interleave this. You can make a 4-element stack in both directions. You interleave in between. But if you go to 3 directions, you cannot do it like that, because you don't have enough space in between not to interfere the antennas between them. So you have to move this mounting point. It has to be moved. It have to be moved back. Okay, have to be moved back. So if you move it back, what happens? You see that you start seeing a ripple in this very nice radiation pattern here. You start seeing a ripple. If you go even further back, yeah, it's only 3 dB. Now here you are 2 meter. Here you are 2 meter away from the phase center, one wavelength away, and you get 3 dB. You get 3 dB distortion. If you go more out, right, like 3 meters, the radiation pattern becomes worse, right? You don't have this 3 dB beam width anymore. These nulls get deeper and so on. So the rule is that the phase center needs to be within circle of 1 wavelength radius, right? So it should be, if you make an array of more than 2 directions, the phase center of the antenna shall not be more than 2 meters away from where you anchor your antenna. So how you mount it, right? You put this, either if it's a square mast, you just make your virtual center of the mounting here. You mount it there, or triangle, or you put it something like that. You should observe this same distance from this virtual or practical vertical axis where you mount the antennas. Okay, and here you would say, okay, but here I have these reflectors are touching, so it can't be done like that. So it can be done by vertically splitting the shift. You shift one stack to the other vertically, just at the middle of the stacking distance. If the stacking distance is 2 meters, you put them 1 meter in between, because in this region there's a minimum electrical field for influencing one antenna to the other antenna, in particular for the tuning or whatever effect. Okay, now how about the phases, right? So we are talking about the phases. So you set up six antenna systems, 6 cables, 6 linear power amplifiers, and this cable is random length. Everything is random length, right? You don't care about the phase. Now, if you would like to care about the phase, how can you get to equal the phases? Okay, the simplest way is you replace your power amplifier with another power amplifier. If you want to keep the same ERRP, the same radiated power as before, it has to be 2 times that power, right? 2P. You have a splitter here, and then equal cable length to your relays and to the antennas. And you will get the same phase here, and you will get this nice radiation pattern as you would like to. Now, if you're already at legal limit here, this is very high power amplifier, so maybe it doesn't work like that. So you can still put 2 amplifiers, but they should be equal, if possible, of equal design, because also through the power amplifier, the phase will change. You can have 2 equal power amplifiers. Maybe the cables are not inside exactly the same. And also, if it's tube amplifier, tuning it will change the phase. If it's solid state, it's more controlled. But still, you can never be sure that if you take 2 exactly equal power amplifiers and put the same power at the output, that the phase will be the same. So ideally, you should measure the phase here. Right? You should measure the phase, still keep the same cables, input cables the same, output cables the same. You measure the phase. If there's any phase difference, you correct it by changing the length of one of these cables at the input. It's relatively simple to change the phase. It's not maybe that simple to measure the phase here, but still it's not too overly complicated. I mean, the simplest one is you have to put 2 directional couplers or 2 probes or whatever kind of probes there, and you put an oscilloscope which can measure 144 megahertz, and you can make this Lissajous curves, or you can just measure the phase between 2 sinusoids and so on. It shouldn't be that problem. And also when you fix that phase during the time, and if amplifiers are already warm enough, that phase wouldn't change. And here we are not talking about the phase need to be exactly 0 degrees. It doesn't matter, right? Because it's not like making interference cancellation when you have to have 180 degrees exactly. Here, even if it's 45 degree, even if it's 90 degree difference, it's still fine, right? Because it will just create about 3 dB nulls, not 10 or 15 dB. So don't be too accurate here, but you should measure and check where you are. Okay, then the part 3. So what will be the ultimate setup for 2 meters? Right, 1 high gain omnidirectional antenna, and then a set of high gain directional antennas. That would be a very expensive setup, and the idea would be that this high gain omnidirectional antenna is built in a way that you can use its parts also for the receiver, for receiving. So the idea is you create this antenna by combining a set of high gain antennas in different directions, which on the receive side you can use each one you select, right? You select each one of them. So how you would design this kind of high gain omnidirectional antenna? So on the receive side it's clear, right? It's gain. You're concerned about the gain. What's your receiver gain? Maybe what's the beam width because of interference or whatever, but you're concerned about the gain. On the transmit side, you're concerned about the ERP, so effectively radiated power. So your idea is that you would keep the ERP the same as you had before with 1 antenna or with 2 antennas. And then here comes way of optimizing, or let's say, making things less over-designed. So your ERP would generally be direction dependent, right? That's probably clear. If you look at the this QSO azimuth chart distribution from S59 Delta Echo Mike for the September contest, you see toward the Switzerland, you see the Alps and Dolomites, we can't work it because they're an obstacle. Also Montenegro, you know, it's behind the yes. Also here we have some agricultural area in Hungarian, I think, no hams or maybe something else. But you go 90BB, it has a bit different diagram. They're more south, so it's concentrated on the north, but still some directions on the south, some big cities like Roma, Brindisi, or Bari, I don't know. You look at DR9A, okay, it's still Oscar Kilo is this direction and Delta Lima, but they have to be operating in all directions. Almost here is some nulls as well, either because of the geographical reasons or because there's no activity there. Yeah, Schwarzwald. And you look at IQ5NN, right? You could say they don't need to radiate in the south, or maybe just a little bit, right? Because they have just two directions on the south. All the rest is on the north. And even on the north, you see they have directions where there's no activity or there's no need to radiate the power there, right? Because it has no effect. You're just spilling your power away. You have just 1, 2, 3, 4 directions where you built your score. And they are very close, angularly separated, right? It depends on the score, yeah, but it's something like that. Yeah, it's not so important for this. No, it's just showing you where you win the contest in which directions, okay? Yeah. So a practical example. So everybody knows what's his reference ERP, right? For somebody in middle of Germany is different than for IQ5NN or for IP0A or for 980BB. Depends how far your region of most QSOs is, right? But let's say you say I'm 18 dBi, that's my reference antenna, which I also want to have the same gain for on the receive side, and legally with power. So this is 80 dBm ERP. Now if you take, I will build a reference antenna out of 4 times 7 element in vertical, and this antenna has a 6 dB angle at 60 degrees, so I need 6 stacks to cover 360 degrees, right? 6 times 60 is 360. And to keep the same ERP, right? That's not for the record, but you need 6 times 1.5 kilowatts. Otherwise, you are reducing your ERP. And how does it look like, for example? So if you put this antenna like that, this is your radiation pattern. It's omnidirectional. You can say it's omnidirectional with plus minus 1.5 dB ripple around, which is negligible. But if you don't have to cover the complete 360 degree, you can just put 5 of them. You can put 4 of them, right? Or you could make some combo of it, like it's now on S59 Delta Echo Mike, right? We have this Oscar Kilo Oscar Mike in phase. We create this kind of pattern, and this 2 times 4 times 5 element wide antennas for Italy, which is like that. So you have you can play with it, but you should take some care. So one thing which I would like to point, if you want to make such a kind of antenna, you are constrained by the phase center. So we said the phase center, which is in the middle of the short Yagi, needs to be 2 meters from the central point of mounting, which means that antenna cannot be 10 meters long because you're already out. So you're limited to somehow 1.5 lambda antenna size. And you should take care that you are mounting it really symmetrically. And the second thing is you should be aware that these angles are important, right? If the angle is 60 degrees, it's 60 degree plus minus maybe 2 degree, but not 70 or 80 or 40. And when you start doing this in practice, you find out that it's not that easy to separate two antennas by 45 degrees because it's hard to measure this 45 degrees. It's not that easy to do it mechanically. And that's all. If there are any questions, I can answer.
What was the legal limit for amateur radio? 1.5 kilowatts?
No, in Italy it's 400 watts, I think, right? In France it's 120 watts.
Could you have 6 1 kilowatt amplifiers for this?
Yeah, you could, yeah, why not? And could you, legally? No, legally, I guess no. Maybe with some special license or something. You can work it out, I guess. Maybe just for competition, yeah, maybe. Yeah.
What should be the height above ground?
The height about the ground.
Are we counting grounding gain?
Yeah, you can count ground gain, but it will not change your azimuth pattern. It will just change your elevation pattern. Now, if you are from Serbia, you should be high above the ground, right? If you're on Snezhnik, you're already 800 or 1,000 meters above the ground, no problem. Even if you're on a high mountain, take care that antenna does not see the plateau of the mountain, right? So put it on the border where it sees the slope down. Now, if you're on in a flat area, you should go high because still ground gain and it's the same like on HF. You create a null in the horizontal pattern is a null, and then you try to do as low angle as possible. So you can do this only by going high with the antennas. In 2 meters, you are easily going by 10 lambda, something you cannot get on HF at all, right? But it's important to be aware of this. If you are on a plain region, to put antennas high enough.
Do you think if you turn antenna to the vertical, it will be shifted and the angle to the
No, it won't change the vertical pattern.
No, can this notch situation you can collect not to be like this?
No, just with the phases you can make it. Yeah, changing this will also change a bit the phase, but there is. You mean?
Yeah.
Why would you do that?
If you do it in the US and Bulgaria, showed to Bulgaria, Romania, they have one notch there. This antenna, if you turn approximately 15 degrees right angle, this notch will be gone because you have collecting the energy from the top on another pattern.
You could. Yeah, you could. Yeah.
No, this is the phase. Not the phase of the line. This is the vertical angle line.
If you turn the antenna vertically to the other antenna, you are getting much more isolation between those two antennas, and the basic line what we have there, they are trying to be all the time smaller.
Okay, but Andy is saying if you would change polarization by 15 degrees of one antenna, that's not a big change. I don't think the phase is plain.
We're doing an E. You have phase shifter of this polarization the same. This means that we can cover the angle which is already have notch. We can move it different kind of the isolation between the pattern of another antenna. The more this happens, because we have a lot of antenna one by one, the effective every time cannot modify these patterns regarding the dimension between the Yagi front to back to move it. You need to lots of test of this one, especially I'm talking about the local drop with the 2 antennas.
Mm-hmm.
We make this test with the ADI on the top of the Cherny Vrh, which is 2,000 meters. And the one mast with the 2 direction, only 40 degrees different the whole direction. We turn the down antenna of the stack 15 degrees, and you opening you find the station which is not need to turn antenna to them. They listening and the pattern same better.
Or maybe this was antenna with vertical, with GP antenna, and then.
We don't know. It's coming from the Romania, from the mountain.
Yeah, but when you're a horizontal polarized antenna, your the response to the vertical would be maybe 20 dB down. If you go 15 degree, it's already maybe just 6 dB down, right? So Maybe it's something like that. Reci, Adame.
Actually, so we assume this presentation to be like a theoretical one.
Mhm.
The only practical connections are with the results, actually, the achieved points.
Yes.
Actually, this is a quite weak point because in that direction we have the activity. So, my question is, can or did somebody measure actually the antenna, real antenna diagram? Because if you are like in real estate as you are, you have to put antennas in between.
Mhm.
Actually, we know, depending on the Q factor of each antenna, the diagram is not as presented. It would be nice to have such a nice diagram, but in practice, it's not the case. So, this is a good presentation to pinpoint the problems, the sports text of the antenna. But actually, do we know the real radiation diagram?
Yeah, it would be good to measure. I agree. I mean, you will, if you look at this, like at this. So you, in practice, you will not get that nice diagram, but you will not get nulls of 15 dB or 20 dB if you don't control the phases. If you don't control the phases, you will get those nulls for 100%. You can't get rid of them. So I can cite, I mean, Henning, DF9IFC was actually saying for the DR9A that at some point they came to this messy situation, a lot of antennas, a lot of power and so on, and they would still score 450K, 460K, something like that. Then they changed, they made this change. So that's their setup is actually 8 antennas of like that. 8 antennas are a bit longer, but right. And after that, they regularly go 550, so about 20% more, right, for them.
Actually, I was listening then on both radio, and we have a feeling that if any big ground station from South Farm Fox came on their side, we could easily make 600,000. As the way we are working.
Yeah,
If you listen there,
I'm not so sure.
you know, first hour, second hour, third hour, in 3 hours we are making lots of QSOs.
Mhm.
Their rate is constant, you know,
Mhm.
like the second speed. Okay, they reach because the activity is really high. The problem is ours. So this is not the same. Compare their situation with our situation.
Outcome is saying you have a limited number of the station you can work. So it is not the HF contest where you can work thousands of the QSOs. If you compare, if you take all the lots from S50C, 90BB, you will see that you have 1,300 stations. So and this is maximum what you can reach from this.
From this region, south of Alps.
If you compare, if you overlap all the QSOs from the DR9 Alpha, S50 Charlie Dan and 0BB, you can actually see the discrepancies, the number of stations you can work Oscar Kilo Delta Lima.
Of course,
Actually, the good example is IP5NM, what you showed, the diagram. Most, 90% of QSOs, they make in 3 directions. Oscar Kilo, Delta Lima, even they have a lot of stations in Italy. But, okay, this is
they are close.
Yeah, but look, the lot of IQ, well, who is the ODX for them? Yeah, this is the more important.
No, but if you look at distribution chart of the QSOs between 980BB and DR9A, no, number of QSOs versus the QRB, it's similar. IQ5NN is different. They have 800 kilometers and the peak at 700, 800. But if you look for a 980BB or DR9A, it's very similar, which means that the contacts they are making are of the same, are as hard as for you, right? They make 800 kilometers QSO. It's not easier for them than for you, right? Or for us. Yeah, tell me, Marco, yes. They are not. That's why you have this radiation pattern. This null is not because of the antenna in general, but because of the, right, but, yeah, but you should take care that that you don't have a null in the direction where you have a lot of population there, right? You should take care about this. So the name of the game here is that your signal should be present all the time when you transmit with equal signal level, so that correspondence on the other side, which have 10 to 20 dB lower power, right? They wait for the fading, right? They wait when the conditions come up for you, and they call you at that time, and you make a QSO. It's not that you would, right? All these QSOs are very asymmetrical, right? We are alligators, how we called it before. Everybody hears us very well. We don't hear, right? So you would like to have even more RX gain, but it's in 2 meters. Then that kind of antenna is then very. I mean, there's some limit also on 2 meters, right?
So that is my next question. Okay, you would like a rather diagram on transmitting side. If with short and broad antennas, we have a lower noise
I mean, there's one.
noise to signal ratio, considering that we have cities around and so on. So what would be the better solution for receiving side?
Yeah.
One transmit antenna and many receive antenna.
No, yeah, I removed that part because there's one quirk on the receive side. So when you make this kind of setup, we set these antennas overlap at 6 dB back off, right? 6 dB angle. So in this, when you use them for the receive, you use them individually, not combined. So in these directions, you have 6 dB less gain on the receive. 6 dB is a lot, right? So you can solve it like DR9A did it. So you combine 2 antennas in phase, so you get 3 dB gain even here in this direction. But it's a technical complication because on the receive side, you need to also take care about the phases. You measure the phases, you combine, and then you have and your selection matrix and all that. But it's a lot of functional blocks that if you want to combine the antennas also on the receive side. The other solution which they had, but they quit, is that in the middle here, like we do have, you have a fully rotatable antenna with high gain, and you take care about these nulls with that antenna when you rotate it when somebody calls you there, right? So, and you would not transmit on this antenna, for example. You use it just for receive, which is weird, right? You set up a very high gain antenna, you say you will not transmit on that antenna, you just receive. It's like on the 160 meters, right? You transmit only on vertical, and you never receive on vertical, right? Why would you receive on vertical? But here, it's a bit different situation.
Practical question is, how many you need to extend the antenna to get 100 kilometer extra inside of the Europe?
Okay, so no, so there are many propagation modes on 2 meters, but the only propagation mode which is always present is troposcatter. Okay, troposcatter, it's 8 dB for each 100 kilometers. So if you are 600 kilometers QSO, you want to make 700, you need 8 dB more system gain. So 8 dB on your receiver or power or whatever. Okay, and the second point is if your horizon is not clear. So every 1 degree of horizon which is obscured by 1 degree is 10 dB lower signal, right? It's 10 dB, it's huge. And if you go to the high hill and you have minus 1 degree clearance, it's 10 dB higher signal level. So these are, and then if you then go to the fading due to troposcatter, it's going in 10, 15, 20 dB. So it's important factor, right? The fading is random, and with this concept, you take care that your transmit signal is not random, and you receive all the time. You wait for this time of the fading that the stations with 5 watts, 900 kilometers come through, and you hear them, right?
Yeah, on Bulgaria, exactly, we make a lot of tests from different locations, and exactly, first it need to be more to the west. Okay, if you're on the Sofia and the hill, the top hill, you extension to the make extra 100 kilometers, you have the 2 by 16 element stack, you make 4 by 16 element stack to get extra 20 QSO better. But
Yeah.
this is extension a lot of the stuff, 20 by 1000.
Yeah.
That means that if you want to go to the Germany is the problem to us. Maximum
Yeah,
extension you want.
from Bulgaria, it's a problem. I agree.
If you take this direction and take more, nearly 10 stations, 20 extra will be good results.
But you can see also from the results, right? The maximum QRB normally, if you exclude the ducting or whatever strange propagation, is about 1,000 kilometers, 1,100 right? So that's the reach for a troposcatter QSOs with our equipment. And our equipment is constrained by transmit gain, right? The transmit gain 1820 dBi, maybe 21 dBi, and you put a lot of power, but still on the receive you cannot. You're constrained about 1,000 kilometers. So if you're 1,000 kilometers away from the area where there's a lot of correspondence, you don't have chance to work them all, right? Marco, you wanted to say something? Right, yeah. And also on the receive side, yeah. Also on the receive side, it's combining. You get everything what you need with this 18, 19 dBi of gain, yeah. Mm-hmm. Yeah, Richard, you wanted to ask something? No. Yeah, no. You're fine.
It's very easy to define the rules if you are listening to the two antennas on your whole system. You have possibilities to listen to the antennas. For example, you listen only to Germany and you add another system which is pointed wherever it is, north or northeast. And when you listen to both of those systems, and you can see clearly in your meter or on the station signal that the signals drop. What we did so in the past when we had switching on only one whiskey, which was allowing us to listen to the same direction, to the many directions at the same time. We don't do that anymore. That we noticed when you chose 2 or 3 directions, listen to the same time, that you are simply killing one of the common signals, and you don't hear.
No,
It means this is the confirmation of your accord, that you create the null.
No, it's not because of the nulls. So this is your antenna. I left the gain here just to show it has 10 dBi of gain. This is antenna that has 10 dBi of gain. If you would use it on the receive, also with all the phases together, you would have a 10 dBi antenna, which is 8 dB below what you were aiming for that direction. So 8 dB is a lot, right? It's a low gain omnidirectional antenna, and then you pick also all the noise, all the interference, all the splatters. That's why it happens. So you never combine, you never listen on all the antennas because you are just listening on low gain antenna, maybe for some short stations, but it doesn't pay off. It's very dangerous. So what you do is you can combine these two antennas. Still you get wide radiation pattern of two antennas, more noise, more interference, but you get this 6 dB, you get back this 6 dB drop of gain on the receive side. But it's complicated. I mean, it's a complication also. Already on the transmit side, there is a complication, right? If you want to keep your ERP as it is, it's a complication because of the phases. On the receive side, it's another level of complication. Maybe it doesn't pay off. Maybe it pays off. It depends, really. For example, on S59WW, so on the receive side, we have a null here, which is important. There are stations for us here, right? So we are aware of this 6 dB drop of gain, and where there's somebody very, very weak, we go with the big antenna listening to him here, right? That's one of the how we do it. On versus Italy, I oriented the antennas in a way that the null is in a direction where there's actually no activity, which is a bit south of Firenze and north of Rome. It's almost zero activity, so we have a 6 dB drop of gain. There we don't care, right? And actually, if I look at the results, unfortunately, we cannot claim SDR9A for 20% more points. For us, it doesn't work. I don't know if it would work for IQ5NN or 90BB. It's very hard to say. But at least you should take care about these TX nulls when you have antennas close together.
By the way, what's the temperature on Yavor? How much noise will you get there?
It's 1 dB noise figure. 1.5. Yeah, in Ljubljana, of course, yeah. But if you're on some top, on a hilltop, depends what your antenna is facing to. So I was measuring from our location the antenna noise diagram azimuthal, and when we go through the across the city of Postojna, of course it's about 6 dB, for example, 7 dB. But on other directions, it's really below 1 dB. Below 1.7 dB or something like that. Yeah. Okay, Mirko? Mirko is gone because we are continuing with the topic which was meant like this panel, I think, discussing about the 2-meter condensing and so on. Let's go. So who's the next one? Who's the first one that? Is there? No, it's on.